Hello everyone, we are Tuấn Hưng Pham and Michael Wallen at the University of Minnesota. Today we would like to talk about RADA, a tool for reasoning about algebraic data types with abstractions. Let's start with the motivation. Algebraic data types are in everywhere. We can find them in any basic data structures, such as lists and trees, and they are also used in some practical applications, such as HTML or XML messages. In addition, algebraic data types are the fundamental part of any functional programming languages. As a result, reasoning about them is an ongoing research topic, and RADA is an open source tool that can reason about algebraic data types. RADA works based on a decision procedure for algebraic data types. The goal of the decision procedure is to reason about data types with certain abstraction functions. In particular, the decision procedure accepts formulas that contain three terms, catamorphisms that can map the data types to some values in decidable theories, and terms in decidable theories such as integer, real, set, boolean. We will discuss catamorphisms in the next slide. The main idea of the decision procedure is that given a formula that contains algebraic data types, we can abstract the data types away by using catamorphisms that map the data types to some values in decidable theories, and then we can use an SMT solver to check the satisfiability of the resulting formula. Before going into details, let's talk about catamorphisms. Catamorphisms are fault functions that map recursive data types into values in decidable theories. Let's consider the case of binary trees. With a binary tree like the one in the figure here, we can map the tree to its height, which is 2 in this case. We can also map the tree to the sum of all of its element values, or the set of all of the element values in the tree. If we call the catamorphism alpha, the three catamorphisms can be defined as follows. For height, alpha of a leaf is 0 and alpha of a node is equal to 1 plus the maximum value of alpha of the left subtree and alpha of the right subtree. Similarly, for sum, alpha of a leaf is 0 and alpha of a node is equal to alpha of the left subtree plus the value of the element stored in the node plus alpha of the right subtree. And similarly, we can write the definition of the set catamorphism. In the next slide, we will use the height catamorphism. The decision procedure works by exploiting the ability to reason about algebraic data types of SMT solvers. It works through repeated unrollings. So the question is what unrollings are. Let's take a look at the figure here. We have some trees and two types of nodes, black and white nodes. For black nodes, we do not know what they are. The only thing we know about them is that they are some trees. For white nodes, we know the element values stored in the nodes. Now suppose that we have a catamorphism alpha t. First, we treat the catamorphism as an uninterpreted function. After one unrolling step, we will try to unroll the definition of the tree so that the catamorphism application will be defined in terms of a white node and two subtrees, which are treated as uninterpreted functions. In the next unrolling step, the two subtrees are unrolled, so on and so forth. Note that after each unrolling step, the maximum depth of a white node will be increased by 1. Let's consider the height catamorphism. First, height t will be treated as an uninterpreted function. However, since an uninterpreted function can return any values in its codomain, and since height t must be non-negative, we add a non-negative constraint to the uninterpreted function. In the next unrolling step, height t is defined as 0 if t is a leaf, or 1 plus the maximum value of height of the left subtree of t and height of the right subtree of t otherwise. Because we need to treat catamorphisms calls otherwise def as calls to uninterpreted functions. We replace height of t left and height of t right as uninterpreted functions. We will continue to use the height example in the next slide. The idea of the decision procedure is that after unrolling the katamorphism to the fx, we first assume that for every tree t where katamorphism alpha t is in the formula is of height less than x. If we get set in this case, then we are done because we are having a complete tree model for the set case. Otherwise, we remove this assumption and check set again. If we get unset, we are also done, because assigning any values to the uninterpreted functions still cannot make the problem set. If it is still not the case, we increase the def x by 1 and repeat the process. Here is an example formula. T is equal to node and height of t is equal to 0. This formula must be unset because if t is a node, its height cannot be 0. Let's see how the decision procedure handles this formula. First, at unrolling def 0, height t is an uninterpreted function. When we use the assumption all the trees are of height less than 0, which is not applicable because there's no such trees. When we do not use the assumption, we get set, but we cannot stop now because we are using uninterpreted functions, so the set result might not be correct. We need to continue the unrolling process. At unrolling def 1, we have the definition of height t as in the previous slide. First, with the assumption we are looking for trees of height less than 1, so t must be a leaf. The formula is unset because t cannot be node and leaf at the same time. We do not stop here because we are using uninterpreted functions, so we need to consider the case with our assumption. Similarly, when we do not use the assumption, the formula is still unset. In this case, no uninterpreted functions are used, and we can conclude that the original problem is unset. The decision procedure is sound for all types of katamorphisms and complete with monotonic katamorphisms. Some examples of monotonic katamorphisms are mapping the tree to the sum of its element values, mapping a tree to its number of internal nodes, and mapping a tree to the set of its element values. Rada is an open source tool that works based on the unrolling based decision procedures. It supports SMT-Lib2 format and both CVC4 and Z3. One example of its applications is in the Gardo system to verify guard applications. Next, we would like to present a demo of the tool.
Here is our website, crisis.cs.umn.edu/RADA, where you can download the tool and also the benchmark examples that we have for the FSE paper. So, available for download, we have the binary, the source code, which is available as an Eclipse archive file, benchmark examples for FSE, and a variety of other benchmark examples. Once you've downloaded the tool, we have instructions as to how to use RADA. Once we have downloaded RADA and we expand the zip files, we get two directories, one that has the tool, one that has the benchmark examples. In the RADA tool directory, we have the jar file and the libraries that RADA uses to execute. In the benchmark examples directory, we have all of the benchmarks that were in the FSE paper that you can run once you download the tool. Okay, now let's actually run RADA. We're going to run RADA on a small example containing tree-shaped data with real valued elements and a katamorphism that sums all of the elements within a tree. In order to run RADA, we're going to create a command prompt and navigate to the directory containing the RADA jar file. Now it's not shown in the video, but if we'd like to run RADA from anywhere in the file system, what we can do is create a batch file or shell script containing the java-jar command, and then adding the directory containing that batch file or shell script into our path. When we run RADA, what we need to do is we need to specify the file that we wish to analyze. And so in this case, it's a file that's in the FSE submission examples directory. And we also have to specify a solver. RADA currently supports either Z3 or CBC4 as the underlying SMT solver. Almost immediately, RADA returns SAT, and we'll take a look at the model and why it returns SAT in just a moment. But first, let's look at command line options for RADA. First is show temp files. So RADA works by iteratively unrolling a catamorphism, and each time it unrolls, it sends a new problem to an SMT solver. So the show temp files shows the temporary files that RADA uses to communicate. We can also ask RADA to provide more information about the solving process. So when we type verbose, what we can tell is the number of unrollings that were necessary to generate the result, and the number of temporary files that RADA generates. Okay, now let's take a look at the sum tree benchmark example that we ran. We declare a data type that has trees of real valued elements. We have a catamorphism, and we're going to put a couple of assertions in, one that defines the structure of the tree, and the second one that checks whether the sum of the elements of the tree is equal to 5. And in this case, that is satisfiable. Now let's look at a bigger example. This is an example from the Gardal program that has 8 mutually recursive data types, 6 catamorphisms, and 17 proof obligations. So the RADA file supports the SMT2lib push and pop syntax. So we can write a single file that contains a set of obligations. And RADA will attempt to successively prove or disprove the satisfiability of each of the obligations. So here we're going to run this more substantial example through the RADA tool. And it's able to work its way through the different obligations in 4 seconds. Now we may want to get more information about the analysis that RADA performed on these obligations. And so we'll run this example again with verbose. And we can see for each of the obligations, it takes a different amount of time and actually requires a different number of unrollings. So RADA also has error handling, as you would expect. If you mistype the solver name, or you use a solver that's not installed in the correct place in your system path, RADA will complain. In addition, if you type the path to the file that you're trying to analyze incorrectly, RADA will tell you about it. And of course, if your RADA file contains syntax errors, it will also give you an error and tell you the line and column number where the syntax error occurred. So let's introduce a syntax error into our example. And when we try and run RADA, it will tell us that we have syntax errors at line 4.
In conclusion, decision procedures for algebraic data types are rapidly advancing, and RADA is an open source tool to reason about the data types.